Welcome. I just want to spend a little bit of time today introducing kinematics, especially displacement, get a little bit into speed versus velocity, and then just do a couple example problems, and if people join in, they can participate as well. So here are just a couple diagrams. These are position diagrams, so X and Y. Initially, we're just going to focus on motion in one dimension. So we've got our professor here who's standing in a certain location, and then she moves to the right to a different location. So you could say, well, how do we describe her motion? A lot of things moved. So her hand, for example, moved from this location up a little bit to this location. So why aren't we concerned about her Y direction motion? But now we're just focused on X direction. And even more so than that, we're really just focusing on her center of mass. So her arm looks like it's extended a little bit farther out from her body in the right-hand diagram than the left-hand diagram. But this really just represents the motion of her center of mass. And later, we may talk a little bit more about center of mass. Essentially, center of mass is if we took all of her mass and located it in just one point. So we could think of if she was a star, all the planets that orbited around her, they would see her mass as just being localized at one point. Same with the sun. If our sun were replaced by a black hole that had the exact same mass of the sun, its volume would be much, much smaller. In fact, physicists aren't sure exactly what the volume would be, but it would definitely be very, very small. It would essentially be a point compared to the sun. But the Earth's orbit would not change if we went to a black hole sun. Of course, we've got a song that addresses that issue. Anyway, so notice we've got this equation here. Delta x equals x final minus x initial. So let's just kind of break that down a little bit. And we're starting off pretty slow in the class. So you might be thinking to yourself, man, we're starting off slow, and then all of a sudden we're just going to really ramp up. And I'll try not to do that, but that does happen because there's going to be a time in anything where you go from being able to understand something to not, and that happens in athletics too. If you're a tennis player, there are certain things you can do. So up to lesson 6, you're really good because that's what you've always done. But then lesson 7 introduces that new thing. You think, man, now all of a sudden it got unbelievably hard in just this one lesson. And no, it's just that you reached the limit of what you could do in tennis. So again, many of you have seen this before. So this here, this means change in. And it's red delta. And what it means is final whatever minus initial whatever. So delta wealth would be final minus initial. So if you started on June 1st, your bank account had $600, and then on July 1st, your bank account had $400, final minus initial, actually, yeah, we'll write it here, would be 400 minus 600. And notice that's actually a negative number. So that means that you lost money, and you probably didn't lose it, you paid bills. In this case, it wasn't a loss. She went from 1.5 meters on the number line to the final value of 3.5. So right here is the start. Maybe this is her desk, for example. So the edge of her desk is at 0. She moved from 1.5 to 3.5, so she moved over final. In this case, 3.5 meters minus initial, 1.5 meters, and that equals 2 meters. What if instead of having the desk here, we would have had the desk in a different location? What if the desk was right here, and we measured the 0 point from right here? Then this, instead of being 3.5, this is going to be to the left of 0. So that is, looks like about, we'll say that's 1.5, but it's to the left of 0, so that's negative 1.5. This over here would then be negative 3.5. So let's see if that x final minus x initial still works. So x final, so she still starts far to the left. She still starts to the left and then moves to the right. So final is, in this case, with the red numbers, minus 1.5 meters. So the delta still means minus here. Minus negative 3.5. So look, we've got negative 1.5 minus a negative 3.5. So that's like saying minus 1. Oops, sorry, that's not a very good looking number there, but it does have a great personality. So negative 1.5 minus negative 3.5, that's like adding 3.5, and we still get 2 meters. So interestingly enough, it doesn't matter where our origin is, whether our origin is here or whether our origin is here, we still get the same value for delta. Her change in position was the same no matter where we start the number line. Here's a slightly different situation. So this is the person's seat. So his center of mass was originally right there. He looks like he has more mass, but his center of mass is still roughly the same location in the body where hers is. Typically, women's center of mass are a little bit lower than men's center of masses. And then he's moved to this location right here. So for this one, we've got delta x equals x final minus x initial. So x initial, it's to sub-0. Some books use a little 0 here. Some books use an initial. A book that I've been using before had a little I there, so I apologize. I need to get into the habit of saying x sub-0. Sometimes stated as x naught. So not being 0, one way to say 0. X final then is 2.0 meters minus x initial, which is 6.0 meters. Notice the number line starts back here, and I'm not sure what is back here. Maybe that's where the restroom is located. And it's very important. Restrooms are often the origin of many issues on an airline. So 2 minus 6 is negative 4 meters. So that's the displacement. Notice displacement has a direction. So this is displacement. Sorry, I touched the magic button on my pen. and that has a direction, and it has a magnitude or a size. And something that has a magnitude and a size, let's use a different color here. Something that has a magnitude and a size, that is a vector. Something that just has a size is a scalar. So mass, for example, is a scalar. Here is an example from the book. So we've got a cyclist riding 3 kilometers west, and then she turns around and rides 2 kilometers east. What is her displacement? So notice that we've got the standard number line orientation here, where east is the positive x direction and west is the negative x direction. So this actually has 2 displacements. There's a delta x1, so we've got this position, starts here. So this position, so they go from here to here. So if this is 0 and this is 3 kilometers away, final, so they're moving in this direction, which is the negative x direction. And then they move to the east, which is in the positive x direction. So they end up 1 kilometer west of where they started, which is in the negative x direction. So the displacement then is -1 meters. They ended up 1 meter away and in the west, which is defined as negative direction. So notice in this case, this signifies the direction, and this signifies how far they are from the starting point. So if we think about that, so what is important here? Well, if you were exercising and you put in your logbook, so let's say you're a runner, so you run a certain distance, you probably just put in your logbook, if you keep a logbook or online, you probably just put the distance you run. You might put something about the environment in which you run, if you ran on a hilly route, or if you ran against the wind, or if you ran downhill or uphill. Then that's probably the important thing. But the most important thing would be how far you actually went. So 1 kilometer is probably not what you would put in your logbook. So you took the long route to your friend's house, you ran by, or maybe you wanted to pick up another friend and then meet at the third friend's house. So you ran to the first friend's house, which is 3 kilometers away, and the 2 of you together ran to your second friend's house. So the distance you ran is 3 kilometers plus 2 kilometers. The friend you picked up only ran 2 kilometers, the lazy person, but they might then run 2 kilometers back. So that's what you'd put in your logbook. Displacement is important if you want to determine locations. So for example, if you tell someone that your displacement was -1 kilometer, they know, and it's agreed upon that west is the negative axis, the negative x-axis. So if it's agreed upon and you say 1 kilometer, that means that you have ran west 1 kilometer. So that tells you the final location. So if somebody knows, oh yeah, that friend of theirs, they live about 1 kilometer west. You must have ran to their house. So this number, the 1 kilometer number, has some meaning. this number has some meaning, and this number has meaning. So they both have meanings. They just give you different bits of information. So let's just do a couple of practice problems here. So we've got 4 different displacements, A, B, C, and D. A couple of these are going to be on different homework assignments. So I'll go over A and B, which is the 2 that I have chosen here. And then we can make up another one that's a little bit more difficult. So distance traveled by A. So A starts at 0. Let's use a color that sort of matches that. This doesn't match it perfectly, but so A starts at 0 and ends at 6. So number 1, which is A. So the distance traveled is equal to 6 meters. Magnitude of the displacement from start to finish. So the displacement, delta x equals x final minus x initial. So final position is 6 meters minus initial position, which is 0 meters. So the displacement is 6 meters, and the magnitude, so here the magnitude of the displacement means absolute value. So the absolute value of delta x in this case is going to be 6 meters, and the displacement is also 6 meters. So if we go to the second one here, so for B, B starts at 12, ends at 8, so the distance traveled is 4 meters. Delta x is final minus initial, so final is 8 meters minus initial, which is 12 meters. So that comes out to be -4 meters. And by the way, I'm just keeping it as one significant digit. There are no decimal points here. So I thought I would just leave it as that. So that is the displacement. The magnitude of the displacement is equal to 4 meters. So let's try a different one here. So let's say we start at, so let's pick a letter E. So we go here to here to here. So letter E, we're starting at 4. So the distance traveled is going to be equal to, so we go 2 meters plus, we're going backwards here, but we're still moving a certain distance. So for running, it doesn't matter if we're running east or west, we're still putting in the miles or the kilometers or the meters in this case. So from 2 to 10 is 8 meters. And then we're going another 2 meters plus 2 meters again, so that is 12 meters. So the distance traveled is 12 meters. The displacement, so x final minus x initial, so finally they end at 8. They started at 4. So that means the displacement is 4 meters, and that's a positive number, so we don't even need to think much about the absolute value, but the absolute value is the same thing. I want to talk a little bit about problem solving and the steps to solving problems. And a lot of books have similar problem solving methods. I'm going to do an example problem in just a little bit that probably won't even be that involved, but we'll try to visit each of these steps. So first, draw a sketch. Typically there's a word problem. In the sketch, could be any number of things. So sketch could include a graph, could include a number line, it definitely includes a representation of the situation. A list of knowns and unknowns. So typically that would be, you'd give a certain value. So if you know that the final position is 2 meters, you know the initial position is 0.5 meters, you know the velocity so average velocity, V stands for velocity. That little bar on the top indicates average velocity, and we'll talk more about this at a later time. Let's say that you know that the average velocity is equal to 4 meters per second, but you don't know what this is. So our knowns are what I actually have a value for. Our unknowns are that which I don't have a value for. The target variable, this is really the unknown that you're solving for. Oops, I almost put an E at the end. It's some sort of a British spelling or something like that. In this case, we only have a single unknown, that I circled in the blue, so there's no ambiguity. Identify relevant equations. So it looks like there's an equation. We'll talk about this a little bit on the next slide. So this equation is a nice one in this case because it has our two knowns. Delta x is really x final minus x initial. So even though I didn't write delta x up here, that still is a known. And then our unknown is delta t. And then determine the algebraic solution and plug in numbers. So this has delta v by itself. Well, we already know delta v. So if we want to solve for delta t, if we want delta t by itself, we can just cross multiply. So delta t equals delta x over average velocity, and then plug in the numbers. So again, this is pretty straightforward. 2.0 minus 0.5 meters divided by 4.0 meters per second. So if we notice what is happening here, let's use a different color. So meters cancels out. We've got seconds in the denominator of the denominator. So that means that seconds is going to pop up to the numerator. So the units are going to be 1 over seconds. That's just from this right here. And that, of course, means seconds. And then 2 minus 0.5, so that's 1.5 over 4. And if we figure what that is going to be 0.3, what is it? Oh, I've got them, I just made these numbers up, 0.375. Seconds. And you could say, well, that's a lot of significant digits here. We really only have 2. You could argue with this one, we only have 1 because this is just sort of a place value. We'll assume that we have at least 2 unless known, so, or unless stated otherwise. So a significant figure is we're going to have delta t equals 0.38 seconds. So check for reasonableness. So something is going a few meters in a few meters per second. So that seems like that's something that would take just a fraction of a second because it's going less than 2 meters and it's going 4 meters per second. So if it can go 4 meters in a second, if it has to go less than 2 meters, it should be taking less than a second. It's going a lot less than 2 meters, so it's going a lot less than a second. So let's go over this one here. A student drove to the university from her home and noted that the odometer reading on the car increased by 12 kilometers. The trip took 18 minutes. What was her average speed? So average speed, speed equals the distance traveled. Oops. Divided by the time taken. So that's going to equal 12 kilometers divided by 18 minutes. And it doesn't ask us for any sort of units, so we could just deal with this right here, that's going to be 12 divided by 18. It's going to be 0.67 kilometers per minute. But if we want to go with kilometers per hour, we know that there are 60 minutes in 1 hour. So that comes out to then be 40 kilometers per hour. If the straight line distance from her home to the university was 10.3 kilometers in a direction 25 degrees south of east, so if we just do a quick sketch of that. So here's east, here's south, so 25 degrees south of east, so that's going to be, let's use a different color here. So maybe right here. So the distance traveled is 12 kilometers, so she maybe went down a road here and then turned right and went down another road, because maybe this is a gigantic park. But a bird, a little tiny bird, could actually fly there directly. So this is the green, and then this is the red. So the straight line distance, so that's the actual displacement. So the green is the displacement. So the average velocity is displacement over duration, change in position divided by change in time. So the displacement is going to be 10.3 kilometers. And if I just said, okay, that's 10.3 kilometers divided by, I've left some information out because displacement also requires a direction. So it turns out that there's a direction here as well. Since delta t does not affect the direction, we're going to keep that out until, because we're going to have to do a little conversion here if we want to convert to kilometers per hour again. So 18 minutes, and actually that arrow is a little bit confusing if I don't do anything with it. Oopsie. So minutes cancel, we end up with kilometers per hour. So that's going to be 34.3. So I'm looking at a calculation that I already did here in my notes because I'm not smart enough to do all this at once to actually figure out numbers on the fly. And now the direction here is going to be 25 degrees south of east. See if she returned home by the same path 7 hours, 30 minutes after she left, what was her average speed and velocity for the entire trip. So this was A, this was B. So for part C, her average speed, this time she went 2 times 12 kilometers divided by 7.5 hours, because it says she returns home 7 hours, 30 minutes after she left. So that doesn't, the 18 minutes is already included in the 7:30. And then the amount of time it took her to drive home, maybe it took her 18 minutes to drive home, maybe it took her less time, who knows? It's a mystery. But we plug in now, and we get 3.2 kilometers per hour. So that's a pretty small number. And it represents a lot of resting time. Because who knows, right? It took her 18 minutes, so if she left at noon, she got there at 12:18, and then left maybe at 7 o'clock or 7:12 or so, and then got home 18 minutes later. So we don't know. Maybe she did a lot of different things. Maybe on the way home she stopped and ate, or stopped and went to the park. So here, her average velocity. So let's think about that one a little bit. She returned home by the same path that she left. So delta x over delta t. So delta x is x final minus x initial. So since I'm doing such a long setup on this, you're probably thinking, there's something weird is going to come up. Well, so her initial position was right there at the origin as I drew it. Her final position, oh, look at that, is also at the origin. So initial position minus final position, they're the same. So that's going to be 0 over delta t, or 0, because x final equals x initial. And I think that is everything. Yeah, I gave myself an extra slide. Wasn't sure if I'd be able to squeeze everything on this slide. You might argue that I didn't do a very good job with that. But anyway, that's displacement. So we went over displacement. We did a couple fairly basic sample problems. We'll definitely be doing more difficult problems in the future. But what you should take from this, just like whenever you're learning a new skill, you learn a new skill in a more simple environment before you learn it in a more difficult environment. So work through each of these steps here when you are doing a problem. Thanks again. I hope that was helpful to you.